Alright, so in this video we're going to talk about the convolution of two functions. This is going to be defined as an integral. This sign right here is the convolution. This is the convolution of f and g. This is going to be a new function of t, and the function that it is going to be defined as the integral from 0 to t of f of y times g of t minus y. So notice that if you add up the arguments of both functions, those add up to t. And so what you're doing is you're really integrating the product of these two functions over the region where, say, x and, I shouldn't use y, but say a and b, where a plus b is equal to t, and where these range, where y ranges from 0 to t. And so what we're really doing, if you think about it, is we're kind of taking a weighted average of these two functions. This convolution is something that comes up a lot in image processing. So convolution is a way to kind of take an average or to blur two functions. So there's this thing called Gaussian blur, which is a convolution of some function with a particular, what's called a Gaussian function, e to the minus x squared, something like that. Anyways, these convolutions come up quite frequently. They're going to be very useful for us in differential equations to solve some differential equation problems, some ordinary differential equations. So this is called the convolution of f and g, sometimes just out of convenience. Sometimes we'll write f convolved with g of t as f of t convolved with g of t. Okay, so that's just really a matter of convenience. So just as a, by way of introduction here, let's talk about a quick example. So if I were to take e to the t and convolve that with sine of t, what we would get, just by the definition, would be the integral of e to the y times sine of t minus y dy. This is not a nice integral, so I'm not going to actually evaluate this anymore. This is not a nice integral, but this is just what the definition is, right? This is just some function of t. That happens to be what the convolution of e to the t and sine of t is defined as. So I want to talk about a few properties of the convolution, specifically in relation to differential equations. The first thing that I want to prove, so I'll call this a proposition. Okay, it's too small to be a theorem. But what I want to do is I want to prove that the convolution is commutative. What that means is that f convolved with g, evaluated at t, is the same as, this is a t, so f convolved with g at t is the same as g convolved with f at t. I should point out that in order for f and g to have a convolution that's well defined, we need a few assumptions on f and g. This is really only defined for, say, continuous functions, or a little bit more generally, you can define this for integrable functions, right? If we can evaluate the integral, then you can evaluate the integral of the product. When I say can evaluate, what I mean is that the integral is a well-defined object if f and g are integrable. Okay, so integrable just means that you can evaluate the integral, or that the integral makes sense. Not necessarily that you can evaluate it in a nice way, just that the integral is a well-defined object. So what we're going to do is I want to prove that the convolution is commutative, and we're going to start by just writing out f convolved with g of t, and that's again the integral of t of f of y times g of t minus y dy. And what we're going to do is just a straightforward substitution. I'm going to let u be t minus y, and then du is going to be minus dy, right? We're integrating with respect to, so we have our differential dy, right? So just notice that we have a dy there. T is a constant, t is our input, so we can treat that like a constant. So du is minus dy. Really, that means that dy is minus du. And then the final thing that we need to do is to change the bounds. Remember that y goes from 0 to t. And if y is 0, then u is t. And if y is t, then u is 0. And so what we end up with is, I guess we actually need one more thing here. If u is t minus y, this tells us that y, so that implies that y is t minus u. And now we're ready to go. So we'll come back and we'll deal with our bounds in a second. We're going to have f of y, so it's f of t minus u, g of t minus y, so that's g of u, dy is minus du, and our bounds flip just based on the substitution that we made. So when y is 0, u is t, and when y is t, u is 0. And then the final step is that we know that we can switch the bounds of the integral at the cost of putting a minus out front. So if we put another minus out front, that makes it a positive, that makes it a plus. And then we have, I'm just going to write this as g of u times f of t minus u. So switching the order is not going to matter here. But this is nothing more than g convolved with f at t. The fact that we're using u's instead of y's is completely inconsequential, right? That's called a dummy variable. Anyways, so it turns out that the convolution is commutative, which is a good thing. I think it's also worthwhile to talk about. The convolution. If I were to take, say, f of t is the constant function 1, and g is arbitrary, then what I want to do is I want to compute f convolved with g. In other words, the function 1, it's important just to remember that this is the function which is identically equal to 1 no matter what t is. No matter what value of t we get, our output is 1. So this is the function 1 convolved with g of t. So this is going to be the integral from 0 to t. We're going to have f of t minus y. But remember, we just said that no matter what our input is, our output is 1. And then g of t is going to be, we can write this a few ways, g of t minus y, or g of y, in fact. Let's write it as g of y, because that's how I thought about it the first time. Okay, so g of y dy. And it turns out that this is going to be the integral from 0 to t, g of y dy. So these integrals are really just convolutions. They're a special case when one of the functions is 1. Notice, I just want to correct one thing that I just said. Not correct, but explain just so that there's no ambiguity here. I originally said what would happen if we put the t minus y part in the 1, in the g part rather than the 1. What we would end up with would be f of y, which is again 1, times g of t minus y. But we know that if we were to do a change of variables, we would end right back up at that integral from 0 to t. Right? All right, the next thing that we're going to prove then is going to be what we call the convolution theorem. Okay, so this is often called, let me just write it like this. This is often called the convolution theorem. And again, remember, this is really a statement about Fourier transforms, but that gives us something in regards to the Laplace transform. Okay, so what we're going to do is I want to prove that if I take the Laplace transform of a convolution, that's the product of the transforms, and this is what we're going to prove. Okay, so the convolution is the thing that when you input it into the Laplace transform, you get out a product of the transforms, and vice versa. I'm actually not going to prove this, the converse, but it turns out that it's true. If I take a product, if I take the Laplace transform of a product, we end up with a convolution. That second direction is a lot harder to prove, so I'm just going to prove the first direction. And what we're going to do is, let's just recall that, so I want to walk through a proof, and let's think about if I take the Laplace transform of f, that's what I mean by capital F of s, that's the integral from 0 to infinity e to the negative st f of t dt. Likewise, if I were to take capital G of s, that's the integral from 0 to infinity, e to the negative st, little g of t, dt. And so what we're going to do is I'm going to attack this from reverse, basically. And I want to compute first the product of capital F and capital G. So I'm going to first compute that product. And this is going to be the product of those two integrals, the integral from 0 to infinity, e to the negative st, f of t dt, times the integral from 0 to infinity, e to the negative st, g of t dt. All right. On second thought, I apologize, let me back up one step here. It's going to be useful to have different variables here. So if I use t for the first one, let me use r for the second one. It's not really going to make a big difference here what the variable is. I just want to use something different. The reason is that in the next step I want to combine these two integrals. So it's going to be the integral from 0 to infinity, integral from 0 to infinity, and we're going to have e to the negative st, f of t, e to the negative sr, g of r, dt dr. So our next step is we're going to combine the exponential terms. I'm also going to switch the order of integration, but we're going to get negative quantity r plus t times s, f of t, g of r, dr dt. Switching the order of integration is just so that the conclusion of the theorem turns out the way that I want it to. It's really inconsequential, but I want to write the convolution. I want to write the convolution with respect to t. Okay, so really it's for no other reason than that, but here we go. So that is our next step, so just an algebra step, and then let's next do a calculus step. So I'm going to substitute u is r plus t, and I'm only substituting in for r, right, because we're integrating with respect to r first. So we're going to integrate, so I'm going to leave the integral with respect to t alone. So we're going to have the integral from 0 to t. We're going to have, let's see, we might as well look at our bounds of integration here. But if r goes from 0 to infinity, let's think about what that tells us about u. So first of all, if r is equal to 0, then u is equal to t. And if r is equal to infinity, in other words, if r tends to infinity, this is an improper integral. So really we would write this as the limit as the upper bound goes to infinity. But if that happens, then u also goes to infinity. So it turns out that our integral is going to be from t to infinity. We're going to have e to the negative us. Let's see, we'll have f of t. And then g of r. R we should just write is u minus t. And finally, I forgot to compute this, but du is equal to dr, because we're integrating just with respect to r. All right, so du is equal to dr, so our dr turns into du. And very good. And so we're already in pretty good shape here. A few things that we need to do next. Notice that we can move the f outside the integral. And if we do that, so if I want, I could really just take this f and literally move it outside that integral if we want. But what we really want to do next, you can do that if you want to. I don't know why I even brought that up. But the thing to think about next is switching the bounds, switching the order of the integral. So we know right now, I think it's just worth writing down, u goes from t to infinity, and t goes from 0 to infinity. And so if we switch the bounds of integration, I'm going to leave the inside alone. So f of t, g of u minus t, du, dt, du. This again is just Fubini's theorem, right? This tells you that you can switch the order of integration as long as your function is nice enough. So let's just assume that our function is nice enough. And let's see, t goes from 0 to u. So t goes from 0 to u. And what else? So t goes from 0 to u. And then u goes from, well, t is gone. So u goes from 0 to infinity. So again, just a little Calc 3, change of the bounds of our integral. And now we're almost done, because this is the integral from 0 to infinity. This e to the negative us, I'm going to just bring out. And then this is the integral from 0 to u, f of t, g of u minus t, dt, du. And finally, what is this inner integral? Well, it's nothing more than the convolution of f and g evaluated at u. And then finally, if I take any function and integrate that against the product of e to the negative su, that's just the Laplace transform of that function. Okay, so it turns out that the product of the transforms is the transform of the convolution of the two functions.